Chapter 1. Before Science. Long before humanity built observatories, laboratories, and universities, people looked out at the world and saw mysteries everywhere. The sun rose each morning and disappeared each evening. Storms appeared without warning. Rivers flooded, seasons changed, and stars moved across the night sky in patterns that seemed both beautiful and strange. People experienced illness, witnessed death, and wondered where life itself had come from. For thousands of years there were no scientific textbooks to consult, and no instruments capable of revealing hidden truths. There were only questions. The desire to understand the world is one of humanity's oldest traits. Even the earliest humans were observers. Long before written history began, our ancestors watched animals, studied weather patterns, and learned to recognize the changing seasons. Survival depended on these observations. A hunter who understood animal behavior had a better chance of finding food. A gatherer who recognized seasonal plants had a better chance of feeding a family. Knowledge was valuable, and over many generations people accumulated vast amounts of practical experience. Yet practical knowledge was not the same as science. People could observe what happened, but often had little understanding of why it happened. When confronted with questions that seemed impossible to answer, nearly every civilization turned to stories. These stories helped explain the world and humanity's place within it. In ancient Egypt, the daily journey of the sun was linked to the god Ra, who traveled across the sky by day and through the underworld by night. In Greece, thunder and lightning were associated with Zeus, king of the gods. In Scandinavia, storms were connected to the mighty Thor. Across Asia, Africa, Europe, and the Americas, myths provided explanations for natural events that people could not otherwise understand. Today, it may be tempting to view these stories as simple superstition, but that would be unfair. Ancient people were trying to solve the same mysteries that scientists investigate today. They lacked modern tools and methods, but they possessed the same curiosity. Mythology was often humanity's first attempt to answer difficult questions. Imagine living thousands of years ago and witnessing a solar eclipse. The sun suddenly begins to disappear. Daylight fades. Birds stop singing. The temperature drops. A shadow moves across the land. Without knowledge of astronomy, the event would seem terrifying. It is easy to understand why many ancient cultures viewed eclipses as supernatural warnings or messages from the gods. What appears obvious to us today was once a profound mystery. Yet even as myths flourished, careful observation continued. Ancient civilizations paid close attention to the natural world because their survival depended on it. Farmers needed to know when to plant crops. Sailors needed to navigate across open water. Priests often tracked the movements of celestial bodies to determine important dates and religious festivals. Over time, people began noticing that nature followed patterns. The moon changed shape in a regular cycle. The seasons returned year after year. Certain stars appeared at predictable times. The more people observed, the more they realized that many events were not random. One of the earliest examples of systematic observation came from Mesopotamia, where scholars carefully recorded astronomical events. For centuries, they tracked the movements of planets, stars, and the moon. Their records became increasingly accurate and helped create some of the world's earliest calendars. In ancient Egypt, priests observed the star Sirius, whose appearance in the dawn sky closely matched the annual flooding of the Nile. Because the Nile flood was essential for agriculture, these observations became enormously important. Accurate predictions could help entire communities prepare for the year ahead. Neither the Mesopotamians nor the Egyptians practiced science in the modern sense. However, they demonstrated something equally important. They observed. They recorded. They looked for patterns. These habits would later become essential parts of scientific thinking. A major turning point occurred in ancient Greece. Around the 6th century BCE, some Greek thinkers began asking whether natural events might have natural explanations. Rather than attributing everything to the actions of gods, they sought causes that could be observed and understood. One of these thinkers was Thales of Miletus. Very little is known about his life, and some stories about him are probably legends. Yet he is remembered because he approached the world differently. Instead of relying entirely on mythology, he searched for rational explanations. He believed nature could be studied and understood through observation. Other Greek philosophers expanded upon this idea. They debated the structure of the universe. They discussed the nature of matter. They debated the structure of the universe. They discussed the nature of matter. They argued about whether everything was made from a few basic substances. Some even proposed that matter might be composed of tiny, indivisible particles, an idea that would eventually resemble the modern concept of atoms. Most of their conclusions were wrong, but that is not what matters. What matters is that they were asking questions in a new way. Instead of accepting traditional explanations without challenge, they were testing ideas through reasoning and debate. This shift may seem small, but it represented one of the most important developments in human history. The earliest roots of science were beginning to emerge. Progress remained slow. Ancient thinkers lacked many of the tools that later scientists would take for granted. There were no telescopes to study distant planets, no microscopes to reveal tiny organisms, no advanced mathematics to describe complex natural processes. As a result, many mysteries remained unsolved. For centuries, scholars continued to speculate about the universe while possessing only fragments of the information needed to understand it. Yet knowledge gradually accumulated. Generation after generation, observations were recorded and preserved. Ideas were debated, mistakes were corrected, new questions emerged. This process was often messy and uneven. Civilizations rose and fell, libraries were built and destroyed, important discoveries were sometimes forgotten for centuries before being rediscovered. But curiosity endured. The desire to understand the world never disappeared. Across different cultures and different eras, people continued asking the same fundamental questions. What is the earth? What are the stars? Why do things fall? What causes disease? How did life begin? The history of science is, in many ways, the history of humanity attempting to answer these questions. What eventually separated science from mythology was not intelligence. Ancient people were just as intelligent as we are. The difference was method. Science developed when people began demanding evidence. An explanation was no longer accepted simply because it was ancient, popular, or supported by authority. Instead, ideas increasingly had to match observations. They had to explain reality, and if evidence contradicted a belief, that belief had to change. This principle seems obvious today, but it was revolutionary. It transformed the pursuit of knowledge. It allowed human understanding to improve rather than remain fixed. Every major scientific breakthrough would eventually depend upon this simple idea. Observe carefully. Question assumptions. Test explanations. Follow the evidence wherever it leads. The journey from mythology to science did not happen overnight. It took thousands of years. It involved countless thinkers, observers, scholars, and dreamers. But once humanity began searching for evidence instead of relying solely on tradition, a new chapter in history opened. The discoveries that followed would reshape civilization. They would reveal the true scale of our world, uncover invisible forms of life, explain the motions of the heavens, and eventually carry human beings beyond the earth itself. The adventure of scientific discovery had begun, and one of its first great triumphs would come from a surprisingly simple question. What shape is the earth? Chapter 2. Discovering Our World. Today, it seems obvious that the Earth is a sphere. Photographs taken from space show our planet as a blue globe floating in the darkness of the cosmos. Every schoolchild learns that the Earth is round, and most of us rarely give the matter a second thought. Yet for much of human history, no one had seen the Earth from above. There were no satellites, no astronauts, no spacecraft. People experienced the world from ground level, where the land beneath their feet appeared flat and unmoving. How, then, did humanity discover the true shape of the Earth? The answer is one of the most remarkable stories in the history of science. Long before modern technology existed, careful observation and logical reasoning allowed ancient thinkers to uncover truths about the world that seemed impossible to know. The story begins with simple observations. Ancient sailors noticed something curious when ships traveled across the sea. As a vessel moved farther away, it did not simply become smaller until it vanished. Instead, the lower parts disappeared first. The hull vanished, then the sails. Finally, the mast disappeared beyond the horizon. When ships approached from a distance, the reverse occurred. The highest parts became visible first. This behavior suggested that the sea was not perfectly flat. Instead, it appeared to curve. Other clues existed as well. Travelers noticed that different stars could be seen depending on how far north or south they traveled. Some stars visible in one region disappeared entirely in another. If the Earth were completely flat, this would be difficult to explain. The ancient Greeks were among the first people to seriously investigate these observations. By the 6th and 5th centuries BCE, several Greek thinkers had begun proposing that the Earth might be spherical. One reason was philosophical. Many Greek scholars believed the sphere represented the most perfect geometric shape, but they also had evidence from nature. One particularly important clue came from lunar eclipses. A lunar eclipse occurs when the Earth passes between the Sun and the Moon, causing the Earth's shadow to fall across the Moon's surface. Greek observers noticed that the shadow was always curved. No matter when the eclipse occurred, the shadow remained round. The simplest explanation was that the Earth itself was round. A spherical object naturally casts a circular shadow. A flat object would not always do so. This observation may seem straightforward today, but it represented a significant step forward in understanding the world. Among the earliest supporters of a spherical Earth was the philosopher Pythagoras, who lived around the 6th century BCE. Later thinkers, including Plato and Aristotle, expanded upon the idea. Aristotle in particular gathered several arguments supporting a round Earth. He pointed to the changing positions of stars, the curved shadow during eclipses, and observations made by sailors. By the 4th century BCE, many educated Greeks accepted that the Earth was spherical. Yet an even greater achievement was still to come. It is one thing to know that the Earth is round, it is another to determine its size. Remarkably, this challenge was solved more than 2,000 years ago. The man responsible was a Greek scholar named Eratosthenes. Eratosthenes lived during the 3rd century BCE and worked in Alexandria, Egypt, one of the greatest centers of learning in the ancient world. He was a mathematician, geographer, astronomer, and librarian. Like many scholars, he was fascinated by the natural world. One day, he learned of an interesting observation from the Egyptian city of Syene, located far to the south. Each year, at noon on the summer solstice, the sun shone directly overhead. Light reached the bottom of deep wells. Vertical objects cast almost no shadow. This meant the sun's rays were striking the earth at a very specific angle. Eratosthenes realized that the same thing did not happen in Alexandria. On the same day and at the same time, vertical objects there still cast shadows. This difference intrigued him. If the earth were flat, sunlight should strike both cities at the same angle. Yet it clearly did not. Eratosthenes proposed a bold explanation. The earth must be curved. He carefully measured the angle of a shadow in Alexandria at noon on the summer solstice. If the distance between Alexandria and Syene represented 1/50th of the Earth's circumference, then multiplying that distance by 50 would reveal the size of the entire planet. Using available measurements, Eratosthenes performed the calculation. His estimate was astonishingly accurate. Modern measurements show that he came remarkably close to the Earth's true circumference, despite having no modern instruments. It remains one of the greatest scientific achievements of the ancient world. Think about what he accomplished. He measured the size of an entire planet using shadows, geometry, observation, and reasoning. He never left Earth. He never saw the planet from space. Yet he discovered its dimensions with surprising precision. His work demonstrated something profound. The universe could be understood through logic and evidence. Questions that seemed impossible could, in fact, be answered. As centuries passed, knowledge of the spherical Earth spread through the ancient world. Although misconceptions occasionally appeared in later periods, educated scholars generally understood that the Earth was round. Contrary to popular myth, most educated people in medieval Europe did not believe the Earth was flat. The idea of a spherical Earth had survived from classical antiquity and remained part of scholarly knowledge. Yet another mystery remained. If the Earth was a sphere, what was its place in the universe? For many centuries, people believed the Earth sat motionless at the center of creation. The sun, moon, planets, and stars were thought to revolve around it. This model seemed sensible. After all, the Earth felt still. The heavens appeared to move. Every day the sun crossed the sky from east to west. Every night the stars did the same. The evidence of the senses appeared clear. Earth stood still while everything else moved. This belief became known as the geocentric model. The most influential version was developed by the Greek astronomer Claudius Ptolemy during the 2nd century CE. His system used complex mathematical calculations to predict planetary movements and remained influential for over 1,000 years. For generations, it provided humanity's best understanding of the cosmos. Yet it was not entirely correct. The realization that the Earth was round had been a major step forward. But humanity's understanding of the universe was still incomplete. Much larger discoveries awaited. The question was no longer simply the shape of the Earth. The question was where the Earth belonged within the cosmos itself. That mystery would challenge some of humanity's deepest assumptions. It would overturn centuries of accepted wisdom, and it would reveal that our planet occupies a far more ordinary place in the universe than anyone had imagined. The next great revolution in science was about to begin, a revolution that would move the Earth from the center of creation and forever change humanity's view of the heavens. Chapter 3: The Solar System Revolution. The Earth beneath their feet appeared solid and unmoving. Every day, the sun rose in the east, crossed the sky, and disappeared in the west. At night, the stars seemed to circle overhead in a great celestial dome. The conclusion appeared obvious. The Earth stood still. Everything else moved around it. This idea became one of the most enduring beliefs in human history. It was accepted by philosophers, scholars, kings, and religious leaders. Entire systems of knowledge were built upon it. For generations, few people saw any reason to question it. Yet the universe was hiding a remarkable secret. The Earth was not the center of everything. In fact, it was moving through space at extraordinary speed, orbiting a star that was itself only one among billions. The discovery of this truth would become one of the greatest scientific revolutions ever achieved. The story begins in ancient Greece. During the 2nd century CE, an astronomer named Claudius Ptolemy created a detailed model of the universe. In his system, the Earth occupied the center, while the sun, moon, planets, and stars revolved around it. At first glance, the model seemed successful. It could explain much of what people observed in the sky. It also matched common experience. No one felt the Earth moving. No one saw obvious evidence that the planet was racing through space. For more than 1,000 years, Ptolemy's system dominated astronomy. Yet it contained a problem. The planets did not always move as expected. Most of the time, planets drifted steadily across the sky. Occasionally, however, they appeared to slow down, stop, and move backward before continuing forward once again. This strange behavior became known as retrograde motion. To explain it, Ptolemy introduced increasingly complex mathematical adjustments called epicycles. Planets moved in circles while simultaneously traveling along other circles. The system worked reasonably well, but it became complicated. As astronomers gathered more observations, additional corrections were needed. The model still functioned, yet many scholars sensed something was not quite right. Then, during the 16th century, a quiet revolution began. A Polish astronomer named Nicolaus Copernicus spent years studying the motions of the heavens. Like many scholars before him, he admired the mathematical elegance of the universe. Yet the existing system seemed unnecessarily complicated. What if the problem was not with the planets? What if the problem was with the assumption that the Earth stood still? Copernicus proposed a radical idea. The sun, not the Earth, occupied the center of the solar system. The Earth was a planet. It traveled around the sun just like the others. This simple change solved many problems at once. Retrograde motion no longer required complicated explanations. Instead, it became a natural consequence of planets moving at different speeds around the Sun. When Earth passed another planet in its orbit, that planet merely appeared to move backward for a time. The effect was an illusion created by motion. Today, this explanation seems straightforward. In the 16th century, it was revolutionary. Copernicus published his ideas in 1543, the year of his death. His work attracted attention, but acceptance came slowly. Many people found the concept difficult to believe. After all, if the Earth was moving, why could nobody feel it? Why did objects not fly off the surface? Why did the stars not appear to shift position dramatically? These questions were reasonable. The evidence was not yet strong enough to convince everyone. The next major breakthrough came from a remarkable observer named Tycho Brahe. Tycho was a Danish nobleman with an obsession for accuracy. Long before telescopes existed, he constructed sophisticated instruments and spent decades recording the positions of stars and planets. His measurements became the most precise astronomical observations ever collected up to that time. Tycho himself never fully accepted Copernicus's model. However, his observations would provide the foundation for someone who did. That person was Johannes Kepler. Kepler inherited Tycho's data after his death and devoted years to analyzing it. At first, he assumed planets moved in perfect circles. After all, circles were traditionally considered the most perfect shape. Yet the data refused to cooperate. No matter how carefully he calculated, the observations would not fit circular orbits. Eventually, Kepler reached a startling conclusion. The planets moved in ellipses. Not circles, ellipses. This insight transformed astronomy. For the first time, planetary motions could be described with remarkable accuracy, using relatively simple mathematical rules. Kepler formulated 3 laws of planetary motion that revealed how planets travel around the Sun. The solar system suddenly became far more understandable. Nature appeared to follow precise mathematical principles. Yet one final piece of evidence was needed to convince the wider world. That evidence arrived through a new invention, the telescope. In 1609, an Italian scholar named Galileo Galilei learned of a device that could magnify distant objects. He quickly built his own improved versions and turned them toward the heavens. What he saw changed history. The moon was not a perfect heavenly sphere. It possessed mountains and valleys. The Sun contained dark spots. Jupiter had moons orbiting around it. And most importantly, Venus displayed phases similar to those of the moon. These observations were devastating for the traditional Earth-centered model. If moons could orbit Jupiter, then not everything revolved around the Earth. If Venus showed phases, it made far more sense within the Sun-centered system proposed by Copernicus. Galileo's discoveries provided powerful support for the new astronomy, yet they also generated controversy. Many scholars remained skeptical. Some religious authorities viewed the new ideas as dangerous because they challenged long-established interpretations of the cosmos. Galileo eventually faced investigation and was forced to publicly recant some of his views. Even so, the evidence continued to grow. Ideas cannot easily be suppressed when observations support them. Over time, more astronomers repeated Galileo's observations. The evidence accumulated, the sun-centered model consistently explained the heavens better than the older Earth-centered system. Gradually, the scientific community accepted the new reality. Humanity's place in the universe had changed forever. The Earth was no longer the center of creation. It was one planet among several orbiting the sun. This realization was about far more than astronomy. It transformed the way people thought about themselves. For centuries, many had assumed humanity occupied a privileged position at the center of existence. The new model suggested something different. The universe was larger than previously imagined, far larger, and humanity occupied only a small part of it. This shift was humbling, yet it was also liberating. If old assumptions could be overturned by evidence, what other secrets might the universe reveal? The scientific revolution gained momentum. Observation and mathematics were proving themselves powerful tools for uncovering truth. Ancient beliefs were giving way to a deeper understanding of reality. But a profound mystery remained. Even if planets orbited the sun, why did they do so? What force guided their movements? What invisible influence held the solar system together? The answer would come from an English scholar whose discoveries would reshape science more profoundly than perhaps anyone before him. His name was Isaac Newton, and his explanation of gravity would reveal one of the fundamental laws governing the universe itself. Chapter 4: Newton and the Laws of Nature. By the middle of the 17th century, humanity's understanding of the universe had changed dramatically. The Earth was no longer believed to be the center of creation. Thanks to the work of Copernicus, Kepler, and Galileo, astronomers had shown that the planets moved around the sun. Careful observation and mathematics were beginning to reveal hidden patterns within nature. Yet one enormous mystery remained. Why did the planets move the way they did? What force guided them through space? What kept the moon from drifting away from Earth? And why did objects fall to the ground in the first place? People had observed falling objects for as long as humans had existed. Every dropped stone, every falling branch, and every raindrop demonstrated that things naturally moved downward, but nobody truly understood why. Ancient philosophers had proposed explanations. Aristotle, whose ideas dominated European thought for nearly 2,000 years, believed that objects moved toward their natural place in the universe. Heavy objects sought the earth, while lighter substances moved upward. His explanations seemed reasonable, but they lacked something crucial: evidence. As scientific thinking developed, scholars increasingly demanded observations and experiments rather than assumptions. One of the first people to challenge traditional ideas was Galileo Galilei. According to a famous story, Galileo dropped objects of different weights from the Leaning Tower of Pisa. Whether the event occurred exactly as described remains uncertain. But Galileo did perform experiments involving motion. His findings were surprising. Aristotle had claimed that heavier objects fall faster than lighter ones. Galileo discovered that this was largely untrue. Ignoring air resistance, objects fall at the same rate regardless of their weight. A cannonball and a stone do not fall differently because one is heavier. They accelerate toward the Earth in the same way. This insight represented a major step forward. Motion could be studied scientifically, it could be measured, it could be described mathematically. Nature appeared to follow rules, yet the deeper question remained unanswered. What caused objects to fall at all? The answer would come from a man who spent much of his life thinking about questions that others considered impossible. Isaac Newton was born in England in 1642, the same year that Galileo died. As a child, he showed a fascination with mechanical devices and problem-solving. He built models, experimented constantly, and developed a reputation for intense curiosity. Yet few could have imagined that he would eventually transform humanity's understanding of the universe. In 1665, a devastating outbreak of plague forced the closure of Cambridge University, where Newton was studying. Like many students, he returned home. What followed became one of the most productive periods in scientific history. Working largely alone, Newton developed ideas that would revolutionize mathematics, physics, and astronomy. One famous story tells of Newton sitting beneath an apple tree when he observed an apple falling to the ground. The tale has often been exaggerated, and the apple probably did not strike him on the head, as later legends claimed. Yet Newton himself confirmed that observing a falling apple helped inspire an important question. Why do objects always fall downward? More importantly, could the same force that pulls an apple to Earth also govern the motion of the moon? This idea was extraordinary. Until then, many people treated earthly events and celestial events as separate phenomena. The heavens seemed fundamentally different from life on Earth. Newton suspected otherwise. He proposed that a single force operated everywhere. The same force that caused an apple to fall also kept the moon in orbit around the Earth. It governed the planets. It governed the stars. It governed the entire universe. That force was gravity. Today, gravity feels familiar. We experience it every moment of our lives. Yet Newton's insight was revolutionary because he transformed gravity from an observation into a mathematical law. He showed that every object in the universe attracts every other object. The strength of that attraction depends upon two factors: the masses of the objects involved and the distance between them. A larger object exerts a stronger gravitational pull. Greater distance weakens the force. This simple idea explained an astonishing number of phenomena. Apples fell because Earth's mass attracted them. The moon orbited Earth because gravity held it in place. Planets traveled around the sun because the sun's enormous mass exerted a powerful gravitational influence. For the first time, the movements of both Earth and the heavens could be explained using the same laws. Nature was unified. Newton presented these ideas in 1687 in a book called Philosophiae Naturalis Principia Mathematica, often known simply as the Principia. Many historians consider it one of the most important scientific works ever written. Within its pages, Newton introduced not only his theory of gravity, but also 3 laws of motion that became foundational to physics. The first law states that an object at rest remains at rest, and an object in motion remains in motion unless acted upon by an external force. This may seem obvious today, but it challenged centuries of thinking. People had often assumed that motion required a continuous force. Newton showed that motion naturally continues unless something interferes. His second law connected force, mass, and acceleration. It provided a mathematical framework for understanding how objects move when forces act upon them. His third law became one of the most famous principles in science. For every action, there is an equal and opposite reaction. When a rocket pushes exhaust gases downward, the gases push the rocket upward. When you walk, your feet push against the ground, and the ground pushes back. The principle appears everywhere in nature. Together, these laws created a new understanding of motion. They allowed scientists to predict the behavior of objects with remarkable accuracy. The universe increasingly resembled a vast machine governed by consistent rules. One of the most impressive demonstrations of Newton's theory involved the planets themselves. Using mathematics, scientists could calculate planetary orbits with extraordinary precision. The motions of celestial bodies no longer seemed mysterious. They followed predictable patterns determined by gravity and motion. For the first time, humanity possessed a framework capable of explaining both the heavens and the earth. Newton's discoveries transformed science. Engineers used his principles to design machines. Astronomers used them to study the cosmos. Physicists used them to investigate the laws of nature. For more than 2 centuries, Newton's work served as the foundation of modern physics. Even today, his laws remain extraordinarily useful. Space agencies use them when launching spacecraft. Engineers rely on them when designing structures and vehicles. Countless technologies depend upon principles Newton helped uncover. Of course, Newton did not solve every mystery. Future scientists would discover situations where his theories required refinement. Albert Einstein, more than 200 years later, would reveal that gravity is even stranger than Newton imagined. Yet Einstein's work built upon Newton's foundation rather than replacing it entirely. Newton had revealed something profound. The universe was not governed by chaos. It was governed by laws. These laws could be discovered, tested, and described through mathematics. The success of Newton's work inspired generations of scientists. If gravity could be understood, perhaps other mysteries could as well. What caused disease? What was matter made of? How did life develop? The scientific revolution accelerated. Humanity had learned that nature followed rules. Now it sought to uncover every one of them. The next great breakthrough would reveal an entire hidden world that had existed all around us from the beginning, a world so small that no human being had ever seen it. A world filled with tiny living organisms that would forever change our understanding of life itself. Chapter 5: The Hidden World. For most of human history, people believed they could see everything important around them. The world appeared straightforward. Animals, plants, rivers, mountains, and stars were all visible to the naked eye. If something existed, surely it could be seen. Yet all around them, in every drop of water, every handful of soil, and even on their own bodies, an invisible world was thriving. A world of tiny living organisms, so small that no human being knew they existed. For thousands of years, this hidden realm remained completely unknown. People observed disease, decay, and fermentation. They watched food spoil. They saw wounds become infected. They witnessed entire communities struck by mysterious illnesses. Yet they had no idea what caused these events. Many explanations were proposed. Some believed disease was a punishment from the gods. Others blamed foul odors or poisonous air. Some thought illnesses spread through mysterious forces that could not be seen or understood. Without the ability to observe microscopic life, these explanations often seemed reasonable. The truth was far more extraordinary. An entire universe of living organisms existed beyond the limits of human sight. The discovery of this hidden world would become one of the most important scientific breakthroughs in history. The journey began not with a famous university professor or a royal scientist, but with a curious Dutch merchant named Antony van Leeuwenhoek. Born in the Netherlands in 1632, Leeuwenhoek had no formal scientific education. He worked in business and spent much of his life dealing with textiles and trade. Yet he possessed an unusual hobby. He became fascinated by lenses. At the time, magnifying glasses already existed, but Leeuwenhoek devoted himself to making lenses of exceptional quality. Through patience and experimentation, he learned how to grind and polish tiny lenses capable of magnifying objects far beyond what most people had ever seen. Eventually, he built small, handheld microscopes that were unlike anything available at the time. When Leeuwenhoek began examining ordinary objects through his lenses, he entered a world no human had ever observed before. He looked at drops of pond water. He examined scrapings from his teeth. He studied rainwater, insects, blood, and plant material. Everywhere he looked, he found life. Tiny creatures swam through water droplets. Minute organisms moved in ways that seemed almost unbelievable. Leeuwenhoek called them animalcules, meaning little animals. Today we know them as microorganisms, bacteria, protozoa, microscopic forms of life invisible to the naked eye. The discovery was astonishing. An entirely new world had suddenly appeared. At first, many people were skeptical. Leeuwenhoek's claims sounded extraordinary. How could countless living creatures exist unseen all around us? Fortunately, other scientists eventually confirmed his observations. As microscopes improved, more researchers began exploring this hidden realm. Again and again they found the same thing. The world was filled with microscopic life. The implications were profound. Humanity's understanding of nature expanded dramatically. For centuries, people had assumed that visible life represented the entirety of creation. Now they realized that vast numbers of organisms existed beyond ordinary perception. The invisible world was not empty. It was alive. Yet despite this remarkable discovery, scientists still did not understand the role microorganisms played in human health. For many years, microscopic life remained more of a curiosity than an explanation. People could see these tiny organisms, but they did not yet know whether they were beneficial, harmful, or completely unrelated to disease. That question would take much longer to answer. Meanwhile, microscopes continued to improve. Scientists began studying cells, the fundamental building blocks of life. They discovered that plants and animals were composed of countless microscopic structures. The more researchers looked, the more complexity they found. Life itself seemed far more intricate than anyone had imagined. By the 19th century, advances in microscopy were revealing astonishing details about living organisms. Researchers could examine tissues, blood, and microorganisms with increasing precision. The invisible world was becoming visible. Yet one mystery remained, especially important. Why did people become sick? Throughout history, diseases had caused immense suffering. Plagues had killed millions. Smallpox devastated populations. Infections claimed lives that today might easily be saved. Despite centuries of observation, the causes of many illnesses remained poorly understood. The answer lay within the microscopic world. Scientists gradually began noticing connections between microorganisms and disease. Certain illnesses seemed associated with particular microscopic organisms. The evidence grew slowly at first. But over time, a revolutionary idea emerged. Perhaps disease was not caused by bad air, supernatural forces, or mysterious imbalances. Perhaps disease was caused by living organisms, tiny invaders entering the body, invisible enemies too small to be seen without magnification. This idea would eventually become known as germ theory. It would transform medicine forever. But before scientists could fully understand disease, they first needed to accept something extraordinary. Human beings did not live alone. Every person existed within a vast ecosystem of microscopic life. Even now, trillions of microorganisms inhabit the human body. Most are harmless. Many are beneficial. Some help digest food. Others assist important biological processes. Life is interconnected in ways that early scientists could never have imagined. The hidden world revealed by the microscope was not merely a scientific curiosity. It was a fundamental part of reality, a hidden layer of existence operating all around us. The discovery of microorganisms marked a turning point in human knowledge. For the first time, humanity realized that important truths could remain completely invisible. Our senses alone were not enough. New instruments could reveal realities beyond ordinary perception. This lesson would become increasingly important as science advanced. Microscopes uncovered the microscopic world. Telescopes revealed distant galaxies. Scientific instruments expanded humanity's vision far beyond the limits of natural senses. The universe proved far larger and far stranger than anyone had suspected. Yet among all these discoveries, few were as immediately important as the hidden world of microscopic life. Understanding it would eventually save millions of lives. It would revolutionize medicine. It would explain some of history's greatest mysteries. And it would lead directly to one of the most important scientific breakthroughs ever achieved. The realization that germs cause disease, a discovery that would fundamentally change the human experience. Many of these revolutions were popular and weirdly mobilizing change the human experience. Chapter 6: Germ Theory and the Revolution in Medicine. For most of human history, disease was one of life's greatest mysteries. People knew that illness could spread through families, villages, and entire nations. They saw epidemics sweep across continents, leaving death and suffering behind. They watched healthy people suddenly become sick, yet they had little understanding of why it happened. Without scientific evidence, many explanations emerged. Some believed disease was a punishment from divine powers. Others blamed bad air, foul smells, or poisonous vapors. This idea, known as the miasma theory, remained popular for centuries. According to this belief, diseases spread through unhealthy air rising from swamps, garbage, and decaying matter. At first glance, the theory seemed reasonable. After all, dirty places often did smell bad. Disease frequently appeared in crowded cities with poor sanitation. The connection between unpleasant conditions and illness was real. The problem was that people had identified the wrong cause. The smell itself was not making people sick. Something else was. The truth would only become clear after scientists began investigating the microscopic world revealed by the microscope. One of the most important figures in this story was a French chemist named Louis Pasteur. Born in 1822, Pasteur initially studied chemistry rather than medicine. His early work focused on fermentation, the process used to make products such as wine and beer. At the time, many scientists believed fermentation happened spontaneously through purely chemical reactions. Pasteur was not convinced. Using microscopes and careful experiments, he discovered that tiny living organisms were responsible for the process. Different microorganisms produced different results. Some helped create useful products. Others spoiled food and drink. This observation led Pasteur to an even more important question. If microorganisms could affect food, could they also affect human health? To investigate, Pasteur performed a series of famous experiments. One involved specially designed flasks with long, curved necks. Nutrient-rich broth was boiled to kill any existing microorganisms. Air could still enter the flask, but dust and microbes became trapped in the curved neck. The result was remarkable. The broth remained free of contamination. No new organisms appeared, but if the flask was tilted, allowing trapped particles to reach the broth, microorganisms quickly began growing. These experiments helped disprove the long-held belief in spontaneous generation, the idea that life could arise from non-living matter without a source. Instead, Pasteur demonstrated that microorganisms came from other microorganisms. Life came from life. The implications were enormous. If invisible organisms existed everywhere and could affect food, perhaps they also played a role in disease. At roughly the same time, doctors were struggling with a horrifying problem. In hospitals across Europe, many women died shortly after giving birth. The condition became known as childbed fever. Some hospitals experienced mortality rates so high that giving birth there could be more dangerous than delivering a child at home. One physician, a Hungarian doctor named Ignaz Semmelweis, noticed something strange. Hospitals where doctors moved directly from performing autopsies to delivering babies experienced far higher death rates than hospitals staffed primarily by midwives. Semmelweis suspected that something invisible was being carried from dead bodies to living patients. He instructed doctors to wash their hands thoroughly before examining mothers. The results were dramatic. Deaths fell sharply. Today, this seems like an obvious solution. At the time, however, many doctors rejected the idea. The concept that physicians themselves might be spreading disease was deeply unpopular. Semmelweis's findings were largely ignored during his lifetime. Only later would science confirm that he had been correct. The next major breakthrough came from a German physician named Robert Koch. Koch sought to identify the specific microorganisms responsible for particular diseases. Through meticulous research, he demonstrated that certain diseases were caused by specific bacteria. He identified the bacterium responsible for anthrax, a deadly disease affecting both animals and humans. Later, he helped identify the bacteria responsible for tuberculosis and cholera. These discoveries transformed medicine. Disease was no longer viewed as a mysterious curse or an imbalance of bodily fluids. It had identifiable causes. Specific microorganisms produced specific illnesses. This idea became the foundation of germ theory. According to germ theory, many diseases are caused by microscopic organisms entering the body and multiplying. Today, this principle seems obvious, but in the 19th century, it represented a revolutionary shift in understanding. Once doctors understood the cause of disease, they could begin developing effective methods of prevention. Hospitals slowly adopted stricter hygiene practices. Hand washing became increasingly common. Medical instruments were sterilized. Clean operating environments became a priority. The results were extraordinary. Mortality rates declined. Survival rates improved. Medical care became safer. One of the greatest beneficiaries of germ theory was surgery. Before the late 19th century, surgery was often extremely dangerous. Even if an operation itself succeeded, infections frequently killed patients afterwards. A Scottish surgeon named Joseph Lister recognized that Pasteur's work on microorganisms could help solve this problem. Lister began using antiseptic chemicals to kill germs on surgical instruments, wounds, and operating areas. The impact was immediate. Post-surgical infections fell dramatically. For the first time, complex operations became significantly safer. Modern surgery was born. The germ theory revolution extended beyond hospitals. Cities improved sanitation systems. Clean water supplies became a public health priority. Sewage systems were expanded. Public health campaigns encouraged hygiene and disease prevention. As these changes spread, life expectancy began rising. Diseases that had once devastated populations became easier to control. The understanding of germs also paved the way for another life-saving innovation: vaccines. Scientists discovered that the immune system could be trained to recognize and fight certain diseases before infection occurred. Vaccination campaigns eventually helped eliminate or drastically reduce some of humanity's most feared illnesses. Perhaps the most remarkable aspect of germ theory is how recently it emerged. For thousands of years, humanity lived without understanding one of the most important causes of disease. The microorganisms responsible for countless illnesses existed all around us, yet remained completely invisible. Only through careful observation, experimentation, and evidence did scientists uncover the truth. The discovery transformed medicine from a field often guided by tradition and guesswork into one increasingly based on scientific understanding. Millions of lives have been saved as a result. Today, whenever a surgeon sterilizes equipment, a doctor prescribes antibiotics, or someone washes their hands to prevent illness, they are benefiting from discoveries made by Pasteur, Koch, Semmelweis, Lister, and countless others. Their work revealed that some of the greatest threats to human health came not from visible dangers, but from microscopic organisms hidden from sight. Yet as scientists explored the invisible world of germs, another mystery was capturing the imagination of researchers across Europe and America. A strange force had been observed for centuries. It could produce sparks. It could attract objects. It could travel through wires and power machines. For a long time, it seemed almost magical. Soon, scientists would begin unlocking its secrets. And in doing so, they would discover the force that would power the modern world. Chapter 7: Matter and Electricity. Today, it is almost impossible to imagine life without electricity. Electric lights illuminate our homes and cities. Computers process information at incredible speeds. Refrigerators preserve food. Telephones connect people across the globe. Trains, factories, hospitals, and entire nations depend upon the continuous flow of electrical energy. Yet for most of human history, electricity was a mystery. People occasionally witnessed its power during thunderstorms when brilliant flashes of lightning split the sky and shook the earth with thunder. They experienced small electric shocks after walking across carpets or touching certain materials. These strange phenomena were known, but nobody truly understood them. Electricity seemed unpredictable, mysterious, and almost magical. The journey toward understanding it would take centuries and involve some of the most brilliant scientific minds in history. The story begins in the ancient world. More than 2,000 years ago, Greek observers noticed that rubbing amber with fur caused the amber to attract lightweight objects such as feathers or bits of straw. The effect was curious but poorly understood. The Greek word for amber was electron, a word that would eventually give us the modern term electricity. For centuries, however, this strange attraction remained little more than an interesting curiosity. It was not until the 17th century that scientists began seriously investigating electrical phenomena. One of the earliest pioneers was an English scientist named William Gilbert. Working in the late 1500s and early 1600s, Gilbert carefully studied magnetism and electrical attraction. He distinguished between magnetic forces and electrical forces, helping establish the foundations of future research. His work encouraged other scientists to investigate these mysterious effects. As experiments continued, researchers discovered that certain materials could accumulate electrical charge when rubbed together. Glass, silk, fur, and amber all displayed unusual properties. Electric sparks could be produced. Objects could attract or repel one another. Yet nobody knew what electricity actually was. The mystery deepened as observations accumulated. By the 18th century, electrical demonstrations had become popular throughout Europe. Scientists and entertainers alike amazed audiences with sparks, shocks, and strange electrical devices. Among those fascinated by electricity was an American printer, inventor, and statesman named Benjamin Franklin. At the time, this idea was not universally accepted. Lightning seemed vastly more powerful than anything produced in a laboratory. Nevertheless, Franklin believed they were manifestations of the same phenomenon. According to a famous story, Franklin conducted a kite experiment during a thunderstorm in 1752. While details of the event have often been exaggerated, the experiment helped demonstrate a connection between lightning and electricity. The realization was profound. A force once associated with divine wrath or supernatural power could now be studied scientifically. Lightning was not magic. It was a natural phenomenon. More importantly, it obeyed predictable laws. Franklin's work eventually led to the invention of the lightning rod, a simple device that protected buildings by safely directing electrical energy into the ground. Countless structures were spared destruction as a result. The study of electricity accelerated. Scientists increasingly realized that electricity could be generated, stored, and manipulated. One major breakthrough came from an Italian scientist named Alessandro Volta. In 1800, Volta created the first practical electric battery. His invention produced a steady flow of electrical current rather than brief static charges. For the first time, scientists had a reliable source of electricity for experiments. The battery transformed research. Electrical investigations that had once been difficult or impossible suddenly became practical. Volta's invention opened the door to an entirely new era of discovery. Soon afterward, a Danish scientist named Hans Christian Ørsted made an unexpected observation. While conducting experiments, he noticed that an electric current could move a nearby compass needle. This seemingly simple observation revealed a profound connection between electricity and magnetism. The two forces were not separate. They were linked. Scientists across Europe rushed to investigate this relationship. Among them was one of the most influential experimental scientists in history. His name was Michael Faraday. Faraday's story is remarkable because he came from humble beginnings. Born into a poor family in London, he received relatively little formal education. As a young man, he worked as a bookbinder's apprentice. While binding books, he read them. Many of those books discussed science. The more he read, the more fascinated he became. Eventually, Faraday secured a position assisting scientists and began conducting experiments of his own. His curiosity and determination proved extraordinary. Faraday discovered that moving magnets could generate electricity. This discovery, known as electromagnetic induction, became one of the most important breakthroughs in technological history. It provided the foundation for electric generators. Today, nearly every large-scale power station on Earth relies upon principles Faraday helped uncover. Whether electricity comes from hydroelectric dams, nuclear reactors, wind turbines, or fossil fuel power plants, the underlying process often involves generating electrical current through electromagnetic induction. Faraday had revealed one of nature's most important secrets. Electricity and magnetism were deeply connected. His discoveries transformed both science and industry. Yet another scientist would soon provide the mathematical framework needed to fully understand these forces. That scientist was James Clerk Maxwell. In the 19th century, Maxwell developed a set of equations describing electricity and magnetism with extraordinary precision. His equations showed that electric and magnetic fields could travel through space as waves. Even more remarkably, he calculated their speed. The result matched the known speed of light. This led to a stunning conclusion. Light itself was an electromagnetic wave. For the first time, electricity, magnetism, and light were united within a single scientific framework. The realization ranks among the greatest achievements in scientific history. What had once seemed like separate phenomena were actually different aspects of the same underlying reality. Scientists now possessed a powerful understanding of electromagnetic forces. The practical consequences were enormous. Inventors quickly began applying these discoveries. Telegraphs allowed messages to travel vast distances almost instantly. Telephones transmitted voices through wires. Electric lighting illuminated streets and homes. Factories adopted electric motors. Entire industries emerged. One of the most famous figures of this era was Thomas Edison, who helped develop practical electric lighting systems and commercial power networks. At the same time, another inventor, named Nikola Tesla, made major contributions to electrical engineering, particularly through his work on alternating current systems. The rivalry between competing electrical technologies became known as the War of Currents. In the end, alternating current proved highly effective for transmitting electricity over long distances, and became widely adopted around the world. By the early 20th century, electricity was transforming civilization. Cities glowed at night. Machines increased productivity. Communication became faster than ever before. The modern technological age had begun. What makes the story of electricity so remarkable is how dramatically it changed human life. For thousands of years, people relied on muscle power, animal labor, wind, water, and fire. Within just a few generations, electrical technology reshaped nearly every aspect of civilization. Few scientific discoveries have had a greater practical impact. Yet while scientists were learning to control electricity, another mystery remained unsolved. What exactly was matter? Everything in the universe, people, animals, plants, oceans, mountains, and stars, was made of something. But what? Ancient philosophers had debated this question for centuries. Now, scientists were finally beginning to uncover the answer. Their investigation would reveal the hidden structure of matter itself and fundamentally change humanity's understanding of the physical world. Chapter 8: Evolution and Deep Time. For most of human history, people believed the Earth was far younger than it actually is. Ancient civilizations developed creation stories to explain the origins of the world. These stories varied from culture to culture, but many shared a common assumption. The Earth had existed for only a relatively short period of time. Mountains, rivers, forests, and oceans were often thought to have appeared much as they are today. At first glance, this seemed reasonable. Human lifetimes are short. Even the oldest buildings and monuments rarely survive more than a few thousand years. Compared to the span of a human life, the world can appear permanent and unchanging. Yet hidden within rocks, cliffs, and fossils was evidence of a far more astonishing reality. The Earth was not thousands of years old. It was unimaginably ancient. And life itself had been changing for hundreds of millions of years. The discovery of this truth would fundamentally alter humanity's understanding of its place in nature. The story began with curious observations made by geologists and naturalists. As people explored mountains and dug mines, they noticed strange objects embedded within rocks. Seashells appeared on mountaintops. Fossilized fish were found far from any ocean. The remains of ancient creatures emerged from stone layers buried deep underground. These discoveries raised difficult questions. How had marine animals reached high mountains? Why were some creatures found only in certain layers of rock? And why did many fossils belong to animals that no longer existed? During the 18th and early 19th centuries, scientists began studying these mysteries systematically. One important figure was the Scottish geologist James Hutton. Hutton carefully examined landscapes and geological formations. He noticed that processes such as erosion, sedimentation, and volcanic activity were constantly reshaping the Earth. More importantly, these processes were extremely slow. A river could carve a valley, wind could wear down mountains, layers of sediment could gradually accumulate on the ocean floor, but such changes required vast amounts of time, far more time than most people had imagined. Hutton reached a revolutionary conclusion. The Earth must be extraordinarily old. Its features could not have formed in only a few thousand years. Instead, geological change occurred gradually over immense stretches of time. Later, the geologist Charles Lyell expanded these ideas. His influential work argued that the same natural processes operating today had shaped the Earth throughout its history. This principle became known as uniformitarianism. The present, Lyell argued, was the key to understanding the past. Mountains, valleys, and coastlines were not the products of sudden supernatural events. They were the result of countless small changes accumulating over millions of years. These ideas transformed geology. The Earth suddenly became much older than previously believed. Scientists were beginning to glimpse what became known as deep time. Yet geology was only part of the story. The fossil record revealed something equally remarkable. Life itself appeared to have changed through time. As researchers examined rock layers, they noticed a pattern. Older layers contained different organisms than younger layers. Some species appeared and then vanished. Others seemed related to modern animals but were clearly distinct. The deeper scientists looked into Earth's history. The stranger the creatures became. Gigantic reptiles, ancient marine organisms, mammals unlike any alive today. The fossil record suggested that life had a history. Species appeared, species disappeared. The living world was not fixed, it changed. Few individuals would play a larger role in understanding this mystery than an English naturalist named Charles Darwin. Born in 1809, Darwin initially showed little sign of becoming one of history's most influential scientists. Yet his life changed dramatically when he joined a scientific voyage aboard a ship called HMS Beagle. The journey lasted nearly 5 years. During that time, Darwin traveled across South America, visited remote islands, and collected thousands of observations about plants, animals, and geology. One location proved especially important: the Galapagos Islands. There, Darwin noticed that closely related species differed slightly from island to island. Certain birds possessed different beaks depending on the food available in their environment. Similar patterns appeared among other animals. At first, these observations seemed puzzling. Why would closely related creatures vary in this way? Over many years of study and reflection, Darwin gradually developed an explanation. The key idea was natural selection. Within every population, individuals vary. Some possess traits that help them survive and reproduce more successfully than others. Those advantageous traits become more common in future generations. Over long periods of time, small changes accumulate. Eventually, entirely new species can emerge. Darwin realized that evolution did not require sudden transformations. It could occur gradually through countless generations. Nature itself acted as a filter, favoring characteristics that improved survival and reproduction. In 1859, Darwin published On the Origin of Species. The book presented overwhelming evidence that species were not fixed and unchanging. Instead, all life shared common ancestry and had evolved over immense spans of time. The reaction was dramatic. Some scientists immediately recognized the power of Darwin's explanation. Others strongly opposed it. The idea challenged deeply held assumptions about the natural world and humanity's place within it. Debates continued for decades. Yet, as evidence accumulated, the scientific case for evolution grew stronger. Fossils revealed transitional forms linking different groups of organisms. Comparative anatomy showed striking similarities among seemingly unrelated species. Later discoveries in genetics would provide even more support. Today, evolution is one of the best supported theories in all of science. It explains the extraordinary diversity of life on Earth, from microscopic bacteria to towering redwood trees, from whales in the oceans to birds in the sky. All living things share a common history, stretching back billions of years. Perhaps the most profound implication of Darwin's work concerned humanity itself. Humans were not separate from nature. We were part of it. Like every other species, we had evolved over time. Our ancestors stretched back through countless generations into the distant past. This realization transformed our understanding of ourselves. Humanity became part of the great story of life rather than standing outside it. Meanwhile, scientists continued refining estimates of Earth's age. During the 20th century, new techniques based on radioactive decay allowed researchers to calculate ages with unprecedented accuracy. The results were astonishing. The Earth is approximately 4.5 billion years old. Life has existed for more than 3 billion years. The age of the dinosaurs ended about 66 million years ago. Modern humans appeared only a tiny fraction of that time ago. If Earth's history were compressed into a single year, all of recorded human history would occupy only the final moments before midnight on December 31st. The scale is almost impossible to comprehend. Yet deep time provides the stage upon which the entire history of life unfolded. The discoveries of geology and evolution revealed a universe far older and more dynamic than anyone had imagined. Mountains rose and fell. Continents drifted. Species evolved and disappeared. Entire ecosystems emerged and vanished. Life was not static. The Earth was not unchanging. Both were part of an ongoing story stretching across billions of years. By the late 19th century, humanity had learned that the world was far older than previously believed, and that life itself evolved through natural processes. But another revolution was approaching. Scientists had begun asking an even deeper question. What is matter actually made of? Discovered? Chapter 9. Einstein and Modern Physics. By the end of the 19th century, science appeared to be nearing completion. Newton's laws explained the motion of planets and falling objects. Engineers were building railways, bridges, and factories using principles that seemed well understood. Electricity was transforming civilization, and scientists had uncovered the ancient history of the Earth and the evolution of life itself. Many physicists believed that only a few minor details remained to be solved. The fundamental laws of nature, it seemed, had already been discovered. Yet hidden within those minor details was a problem that would overturn humanity's understanding of space, time, matter, and reality itself. For centuries, scientists had struggled to understand exactly what light was. By the late 19th century, the work of James Clerk Maxwell had shown that light was an electromagnetic wave. His equations described electricity, magnetism, and light with remarkable accuracy. But they contained a strange implication. According to Maxwell's calculations, light always traveled at the same speed, approximately 300,000 kilometers per second. This created a puzzle. Most speeds depend on the observer. If a train passes you at 100 kilometers per hour, someone standing still and someone moving in another train will measure different speeds. Scientists assumed light should behave the same way. Yet experiments suggested otherwise. No matter how researchers measured it, light always appeared to travel at the same speed. The result made no sense within the framework of classical physics. Something fundamental was missing. The solution arrived from a young patent clerk working in Switzerland. His name was Albert Einstein. Born in Germany in 1879, Einstein was fascinated by physics from an early age. As a teenager, he often imagined strange thought experiments. What would happen if you could ride alongside a beam of light? What would the universe look like? Questions like these occupied his mind for years. In 1905, Einstein published a series of papers that would later be called his miracle year. One of those papers introduced the theory of special relativity. Its central idea was astonishing. The speed of light is always constant, regardless of the observer's motion. To make this possible, space and time themselves had to change. This was a radical departure from centuries of thinking. Most people assume space and time are fixed and absolute. A second is a second. A meter is a meter. The universe provides a single, universal clock. Einstein showed that reality is stranger than that. Time can slow down. Distances can shrink. Events that appear simultaneous to one observer may not appear simultaneous to another. These effects are normally invisible in everyday life because they become significant only at extremely high speeds. Yet they are real. Experiments have confirmed them countless times. One of the most famous consequences of special relativity is time dilation. According to Einstein's theory, time passes more slowly for objects moving at very high speeds. Imagine identical twins. One remains on Earth while the other travels through space at enormous speed. When the traveling twin returns, less time will have passed for them. They will actually be younger than their sibling. This sounds like science fiction, yet it follows directly from Einstein's equations and has been confirmed through precise measurements. Time is not as absolute as it appears. Another surprising result emerged from Einstein's work. Mass and energy are connected. This relationship is expressed by perhaps the most famous equation in history. E equals sign mc 2. The equation states that mass can be converted into energy and energy into mass. Even a tiny amount of matter contains an enormous amount of energy. At the time, few people fully understood the implications. Decades later, this principle would lead to both nuclear power and nuclear weapons. Yet Einstein's revolution was only beginning. Special relativity explained objects moving at constant speeds, but it did not fully explain gravity. Newton had described gravity as a force acting across space. His theory worked extraordinarily well, but Einstein suspected a deeper explanation existed. For nearly 10 years, he worked on the problem. In 1915, he introduced general relativity. The theory completely transformed humanity's understanding of gravity. According to Einstein, gravity is not really a force in the traditional sense. Instead, massive objects bend the fabric of space and time. Imagine placing a heavy ball on a stretched sheet. The sheet sags around the ball. Smaller objects moving nearby naturally follow curved paths. Einstein proposed that something similar occurs throughout the universe. The sun bends space-time around itself. The Earth follows a curved path through that distorted geometry. Planets orbit stars not because they are being pulled by an invisible force, but because they are moving through curved space-time. The idea was breathtaking. Gravity became a property of the structure of the universe itself. Many scientists initially doubted the theory. The mathematics was difficult and the predictions seemed strange. Then came a crucial test. Einstein's equations predicted that gravity should bend light. During a solar eclipse in 1919, astronomers measured the positions of stars near the sun. The observations matched Einstein's predictions. Almost overnight, he became one of the most famous scientists in the world. General relativity passed its first major test. Over the following decades, additional evidence continued to support Einstein's theory. One of the most remarkable predictions involved black holes. Einstein's equations suggested that under certain conditions, gravity could become so powerful that nothing, not even light, could escape. For many years, black holes seemed like mathematical curiosities rather than real objects. Today, we know they exist throughout the universe. Some form when massive stars collapse. Others reside at the centers of galaxies, containing millions or even billions of times the mass of the Sun. In 2019, humanity even captured the first image of a black hole's shadow, providing dramatic confirmation of predictions rooted in Einstein's work. General relativity also transformed cosmology, the study of the universe as a whole. When scientists applied Einstein's equations to the cosmos, they discovered something unexpected. The universe was not static. It was changing. Observations eventually revealed that distant galaxies are moving away from one another. The universe is expanding. This discovery led to the development of the Big Bang theory, which proposes that the universe began in an extremely hot and dense state billions of years ago. Einstein's work had helped open an entirely new chapter in our understanding of the cosmos. Yet his influence extended beyond astronomy. Relativity affects technologies we use every day. GPS satellites orbiting Earth experience measurable differences in time compared to clocks on the ground. Without corrections based on Einstein's theories, navigation systems would quickly become inaccurate. The smartphone in your pocket depends in part on principles developed by Einstein over a century ago. This is one of the remarkable features of scientific discovery. Ideas that initially appear abstract often become essential parts of daily life. What began as an attempt to understand light and gravity eventually influenced communication, navigation, energy production, and modern technology. Einstein's theories revealed that reality is far stranger than common sense suggests. Space can bend, time can stretch. Mass and energy are interchangeable. Black holes can trap light. The universe itself can expand. The comfortable world imagined by 19th century physics had vanished. In its place emerged a cosmos more mysterious and more fascinating than anyone had anticipated. Yet even as physicists transformed our understanding of space and time, biologists were uncovering another profound secret. Hidden within every living cell was a code, a set of instructions that determined how organisms grow, function, and reproduce. The discovery of that code would become one of the greatest scientific breakthroughs of the 20th century. It was the discovery of DNA. Chapter 10: The Secret of Life. By the beginning of the 20th century, scientists had transformed humanity's understanding of the universe. They had discovered that the Earth orbited the Sun, that gravity governed the motion of planets, that microorganisms caused disease, and that life had evolved over immense spans of time. Yet one of the greatest mysteries of all remained unsolved. How does life pass its characteristics from one generation to the next? Why do children resemble their parents? Why do certain traits appear repeatedly within families? And what hidden instructions allow a single fertilized cell to develop into a complete living organism? For thousands of years, nobody knew the answers. People understood that inheritance existed. Plant breeders cultivated crops with useful characteristics. Everyone could observe that offspring often resembled their parents. Yet the mechanism behind inheritance remained a mystery. The first major breakthrough came from an unlikely source. In the mid-19th century, an Austrian monk named Gregor Mendel began conducting experiments in the garden of his monastery. Mendel was interested in how traits passed between generations. To investigate, he carefully bred pea plants with different characteristics. Some plants produced yellow peas, others green. Some were tall, while others were short. Over many years, Mendel recorded thousands of observations. Eventually, he discovered that inheritance followed predictable patterns. Traits did not blend together randomly, as many people assume. Instead, they were passed through discrete units that we now call genes. Mendel's work was revolutionary. Unfortunately, almost nobody noticed. His findings were published, but received little attention. The scientific community largely ignored them during his lifetime. Only decades later would researchers realize how important his discoveries truly were. As the 19th century progressed, scientists increasingly focused on cells, the microscopic building blocks of life. Advances in microscopy revealed that every living organism was composed of cells. Within those cells, researchers noticed mysterious structures called chromosomes. Scientists suspected chromosomes played a role in inheritance, but exactly how remained unclear. The search for the secret of heredity intensified. By the early 20th century, evidence pointed toward a molecule found inside cells. This molecule was known as deoxyribonucleic acid. Today, we simply call it DNA. At first, many scientists doubted that DNA could be responsible for inheritance. The molecule seemed too simple. Proteins appeared far more complex, and therefore seemed more likely candidates. But as experiments accumulated, the evidence became increasingly difficult to ignore. In 1944, researchers demonstrated that DNA carried genetic information. This was a major breakthrough, but an even bigger question remained. How did DNA actually work? What was its structure? How could a molecule store the instructions needed to build and maintain a living organism? The answer would become one of the most famous discoveries in scientific history. In the early 1950s, several research teams were racing to solve the puzzle. Among them were two scientists working in Cambridge, England, James Watson and Francis Crick. At the same time, other researchers were making crucial contributions, including Rosalind Franklin and Maurice Wilkins. Franklin, an expert in X-ray crystallography, produced extraordinarily detailed images of DNA. One particular image, known as Photo 51, provided critical clues about the molecule's structure. Using available evidence, Watson and Crick proposed a model in 1953 that would transform biology forever. DNA, they suggested, consisted of two strands twisted around one another in the shape of a double helix. The structure resembled a spiral staircase. The sides of the staircase were composed of sugar and phosphate molecules. The steps consisted of pairs of chemical bases. These bases followed specific pairing rules. A always paired with T, C always paired with G. At first glance, the structure was elegant, but its true brilliance lay in what it revealed about inheritance. Because each strand contained complementary information, DNA could be copied accurately. When cells divided, the genetic instructions could be passed to new cells with remarkable precision. The mystery of heredity was finally beginning to make sense. DNA functioned as a biological information system. Within its sequence of chemical bases lay the instructions needed to build every living organism. The same basic molecule existed in bacteria, plants, animals, and humans. All life on Earth used the same genetic language. This discovery provided powerful evidence for evolution and common ancestry. It suggested that every living thing was connected through a shared biological history. As scientists learned more about DNA, they uncovered increasingly astonishing details. Genes contained instructions for building proteins. Proteins carried out many of the essential tasks required for life. The sequence of DNA determined which proteins an organism could produce. In a sense, DNA functioned like an enormous instruction manual written using a four-letter chemical alphabet. The human genome contains roughly 3 billion base pairs. Packed within nearly every cell of the body is enough information to fill thousands of books. Yet all of it fits within a microscopic nucleus invisible to the naked eye. The discovery of DNA transformed biology. Researchers could now investigate diseases at the genetic level. Inherited disorders became easier to understand. Scientists began studying how mutations influence health and development. Medicine entered a new era. One of the most significant achievements occurred in 2003 with the completion of the Human Genome Project. This international effort successfully mapped the entire human genetic code. For the first time, humanity possessed a detailed blueprint of its own biological instructions. The project represented one of the largest scientific collaborations ever undertaken. Its results continue to influence medicine, biology, and genetics today. DNA research has also revealed surprising connections between living organisms. Humans share a large percentage of their genes with many other species. We share genes with chimpanzees, mice, fish, plants, and even certain microorganisms. These similarities reflect our shared evolutionary history. The tree of life is far more interconnected than earlier generations could have imagined. Modern genetics has produced remarkable technologies. Scientists can identify individuals through DNA analysis. Ancient genomes can be reconstructed from fossil remains. Researchers can trace human migrations across thousands of years. Doctors increasingly use genetic information to guide medical treatments. Entire fields of science now depend upon discoveries that began with a simple question about inheritance. Yet the story of DNA also reminds us how science often works. No single individual solved the mystery alone. Progress emerged through the efforts of many researchers working across decades. Each discovery built upon earlier work. Mendel's peas, microscopic observations of chromosomes, chemical experiments, X-ray images, mathematical models. Together they revealed one of nature's deepest secrets. The discovery of DNA allowed humanity to understand the language of life itself. It explained how information passes from generation to generation. It illuminated the mechanisms behind evolution. And it opened entirely new possibilities for medicine and biotechnology. Yet even as scientists uncovered the code hidden within living cells, humanity was preparing for another extraordinary achievement. For thousands of years, people had gazed at the stars and wondered what lay beyond Earth. Now, for the first time in history, technology was making it possible to find out. The next great scientific adventure would carry human beings beyond their home planet and into the vastness of space. Chapter 11. Into Space. For nearly all of human history, the sky was a place of mystery. People watched the sun rise and set. They observed the changing phases of the moon and traced the movements of planets across the night sky. Ancient civilizations built monuments aligned with celestial events and created myths to explain the stars above them. Yet no matter how carefully people observed the heavens, one fact remained unchanged. Humanity was trapped on Earth. The moon, planets, and stars seemed forever beyond reach. For thousands of years, the idea of traveling into space belonged entirely to the realm of imagination. Writers dreamed about journeys to the moon. Philosophers speculated about other worlds. Inventors proposed fantastical machines capable of flying beyond the atmosphere. But dreams alone could not overcome gravity. To leave Earth, humanity needed a new technology. That technology was the rocket. The basic principle behind rockets had been known for centuries. Early forms were developed in China, where gunpowder-powered rockets were used for warfare and celebrations. These devices demonstrated an important idea. A rocket could propel itself by expelling material in the opposite direction. The principle follows Newton's third law of motion. For every action, there is an equal and opposite reaction. When a rocket ejects hot gases downward, those gases push the rocket upward. Simple in theory. Extremely difficult in practice. Reaching space required speeds far greater than anything previously achieved. During the late 19th and early 20th centuries, several visionaries began studying the problem seriously. One of the most important was a Russian schoolteacher named Konstantin Tsiolkovsky. Tsiolkovsky never built rockets himself, but he developed many of the mathematical principles that would later make spaceflight possible. He realized that powerful rockets using liquid fuel could potentially escape Earth's gravity. At the time, his ideas seemed almost impossible. Yet they provided the foundation for future developments. Elsewhere, inventors such as Robert Goddard in the United States and Hermann Oberth in Europe began experimenting with rocket technology. Goddard successfully launched some of the world's first liquid-fueled rockets during the 1920s. His work demonstrated that practical rocket flight was achievable. Still, space remained far away. The technology needed further development. Unfortunately, much of that development occurred during a dark chapter of human history. During World War II, Germany invested heavily in advanced rocket research. Engineers developed the V-2 rocket, the first human-made object capable of reaching the edge of space. Although created as a weapon, the V-2 demonstrated that spaceflight was technically possible. When the war ended, both the United States and the Soviet Union recruited German rocket scientists and accelerated their own programs. A new competition was beginning. The Cold War. The United States and the Soviet Union competed politically, economically, militarily, and technologically. Space quickly became one of the most important arenas of that competition. Each nation sought to demonstrate scientific superiority. The race to space had begun. The first major milestone arrived on October 4, 1957. On that day, the Soviet Union launched a small satellite called Sputnik 1. The satellite was simple by modern standards. It carried no cameras, no scientific laboratories, no astronauts, yet its significance was enormous. For the first time in history, a human-made object orbited the Earth. Humanity had entered the space age. Around the world, people listened to Sputnik's radio signals as it passed overhead. Many were amazed. Others were alarmed. The event demonstrated that rockets capable of launching satellites could also potentially launch weapons across continents. The space race intensified. Soon afterward, the Soviet Union achieved another historic first. In 1961, a young pilot named Yuri Gagarin became the first human being to travel into space. Aboard the spacecraft Vostok 1, Gagarin orbited the Earth and safely returned home. His flight lasted less than 2 hours. Yet it changed history. For the first time, a human being had left the planet. Gagarin later described seeing Earth from space as an unforgettable experience. The planet appeared beautiful, fragile, and isolated against the darkness of the cosmos. The achievement stunned the world. The Soviet Union had taken an early lead in the space race. The United States responded with determination. In 1961, John F. Kennedy announced an ambitious goal. Before the decade ended, the United States would land a human on the moon and return them safely to Earth. At the time, this objective seemed almost impossible. No one had yet traveled beyond Earth orbit. The necessary technology did not fully exist. Yet enormous resources were devoted to the effort. Thousands of scientists, engineers, mathematicians, and technicians worked toward a common goal. The result was the Apollo program. Throughout the 1960s, NASA developed increasingly sophisticated spacecraft and rockets. Astronauts learned how to operate in space. Engineers solved countless technical challenges. Several missions experienced failures and setbacks. One tragedy occurred in 1967 when 3 astronauts died during a ground test of Apollo 1. The loss reminded everyone how dangerous space exploration remained. Yet the program continued. Finally, on July 16, 1969, Apollo 11 launched toward the moon. Millions of people around the world watched with anticipation. 4 days later, the lunar module Eagle descended toward the lunar surface. Inside were astronauts Neil Armstrong and Buzz Aldrin. As the spacecraft approached the moon, fuel reserves ran dangerously low. Armstrong manually guided the module to a safe landing site. Then came one of the most famous moments in human history. On July 20th, 1969, Armstrong stepped onto the lunar surface. His first words became legendary. "That's one small step for man, one giant leap for mankind." For the first time, human beings stood on another world. The achievement represented the culmination of centuries of curiosity, decades of scientific progress, and years of extraordinary effort. Over the following years, additional Apollo missions explored the moon. Astronauts collected rocks, conducted experiments, and expanded humanity's understanding of our nearest celestial neighbor. Yet the moon landings were only the beginning. Scientists soon turned their attention to the rest of the solar system. Robotic spacecraft visited planets that had previously existed only as distant points of light. Missions explored Mars, Venus, Jupiter, Saturn, Uranus, and Neptune. One of the most remarkable was the Voyager program. Launched in 1977, the twin spacecraft Voyager 1 and Voyager 2 traveled farther than any previous human-made objects. They provided stunning images of distant worlds and continued transmitting data even today as they journey through interstellar space. Space telescopes transformed astronomy. The Hubble Space Telescope revealed galaxies billions of light-years away and helped refine estimates of the universe's age. Later observatories expanded humanity's vision even further. The universe appeared larger and more complex than ever before. Meanwhile, astronauts continued living and working in space. The International Space Station became a permanent laboratory orbiting Earth, where scientists conduct experiments impossible to perform on the ground. Humans have now spent years continuously living in space. What once seemed impossible has become routine. Yet many challenges remain. No human has traveled beyond the moon since the Apollo era. Mars remains unexplored by astronauts. The distances between stars are still vastly beyond current capabilities. Even so, the progress achieved within a single century is astonishing. Humanity went from powered flight to lunar landings in just 66 years. We sent robots across the solar system. We placed telescopes above Earth's atmosphere. We learned to live and work in orbit. The dream of spaceflight became reality. Perhaps the most important lesson from space exploration is perspective. Photographs of Earth taken from space reveal a small blue world suspended in darkness. No borders are visible, no nations, no divisions, only a fragile planet carrying all known life. The view has changed how many people think about humanity's place in the universe. We are explorers living on a tiny world, orbiting an ordinary star in a vast galaxy. And despite everything we have discovered, the cosmos still holds countless mysteries. In fact, some of the greatest mysteries remain unsolved even today. What is most of the universe actually made of? Why is the universe expanding? And are we alone among the stars? These questions lead us to the frontier of modern science, where the next great discoveries may already be waiting. Chapter 12. The Unfinished Universe. As the 20th century drew to a close, humanity had achieved extraordinary things. We had mapped the planets, decoded DNA, harnessed electricity, landed on the moon, and uncovered the laws governing gravity and motion. Scientific discoveries had transformed civilization beyond anything previous generations could have imagined. Yet something unexpected happened. The more scientists learned, the more mysteries they discovered. Instead of reaching the end of knowledge, humanity found itself standing at the edge of even greater unknowns. Some of the biggest questions in science remain unanswered today, and the answers may change our understanding of reality as profoundly as any discovery that came before. One of these mysteries concerns the universe itself. For centuries, people believed the cosmos was static and unchanging. Then, in the early 20th century, astronomers discovered that distant galaxies are moving away from us. The universe is expanding. This was a revolutionary realization. If galaxies are moving apart today, then they must have been closer together in the past. Following this idea backward led scientists to a remarkable conclusion. The universe appears to have begun approximately 13.8 billion years ago in an event known as the Big Bang. The term can be misleading. The Big Bang was not an explosion in space. It was the rapid expansion of space itself. At the beginning, the entire observable universe existed in an extremely hot, dense state. As space expanded, matter formed. Stars ignited, galaxies emerged, and eventually planets appeared. Everything we see today traces its origins back to that ancient beginning. The evidence supporting the Big Bang is overwhelming. Astronomers observe galaxies moving away from one another. They detect a faint glow of radiation filling the universe, known as the cosmic microwave background. This radiation is essentially the afterglow of the early universe. The distribution of galaxies and the abundance of chemical elements also match predictions made by Big Bang theory. Yet despite its success, the theory leaves many questions unanswered. What caused the Big Bang? What existed before it? Did time itself begin at that moment? Scientists do not yet know. Some of the deepest mysteries lie beyond the limits of current understanding. Another puzzle emerged when astronomers studied galaxies more carefully. According to the laws of gravity, galaxies should not behave the way they do. The visible stars simply do not provide enough mass to hold galaxies together. Yet galaxies remain intact. Something else appears to be contributing additional gravity. Scientists call this invisible substance dark matter. Dark matter cannot be seen directly. It does not emit light. It does not reflect light. It interacts very weakly with ordinary matter. Yet its gravitational effects are unmistakable. Observations suggest that dark matter makes up roughly 27% of the universe. Ordinary matter, the stars, planets, oceans, mountains, and people we can see, accounts for only about 5%. This means most of the matter in the universe is something we still do not understand. The mystery becomes even stranger. In the late 1990s, astronomers discovered that the expansion of the universe is accelerating. Gravity should gradually slow the expansion. Instead, distant galaxies are moving apart faster and faster. Something appears to be pushing the universe outward. Scientists call this unknown phenomenon dark energy. Dark energy may account for nearly 68% of the universe. Combined with dark matter, it means that approximately 95% of the cosmos consists of things we do not fully understand. This realization is astonishing. After centuries of scientific progress, humanity has discovered that most of the universe remains mysterious. The more we learn, the more we realize how much remains unknown. Meanwhile, physicists face another challenge. Two of the greatest scientific theories ever developed describe nature extraordinarily well. Einstein's theory of general relativity explains gravity and the large-scale structure of the universe. Quantum mechanics explains the behavior of atoms, particles, and the microscopic world. Both theories have been tested repeatedly and produce remarkably accurate predictions. The problem is that they do not fit together perfectly. General relativity describes gravity as the curvature of space-time. Quantum mechanics describes reality in terms of probabilities and subatomic particles. Each works brilliantly within its own domain. Yet when scientists attempt to combine them, mathematical difficulties arise. A unified theory capable of describing everything remains elusive. Physicists have spent decades searching for solutions. Ideas such as string theory and quantum gravity attempt to bridge the gap. So far, however, no definitive answer has emerged. One of the greatest goals in modern physics remains the search for a theory that unites all fundamental forces of nature. The mystery of life also continues. The discovery of DNA revealed how biological information is stored and transmitted. Yet scientists still seek answers to profound questions. How did life first arise from non-living matter? What exactly is consciousness? How does the human brain generate thoughts, emotions, and self-awareness? The brain contains roughly 86 billion neurons connected through trillions of synapses. It is arguably the most complex object known in the universe. Despite major advances in neuroscience, many aspects of consciousness remain poorly understood. Why do we experience subjective awareness at all? Why does the brain produce a sense of self? These questions continue to challenge scientists and philosophers alike. Then there is perhaps the most captivating question of all. Are we alone? For most of history, humans had no way to investigate this possibility. Today, the situation is different. Astronomers have discovered thousands of planets orbiting other stars. Many appear to reside within regions where liquid water could potentially exist. The Milky Way galaxy alone may contain hundreds of billions of stars. Across the observable universe, there may be trillions of galaxies. The numbers are difficult to comprehend. Given such vastness, many scientists suspect that life may exist elsewhere. Yet despite decades of searching, no confirmed evidence of extraterrestrial life has been found. The silence itself has become a mystery. This puzzle is sometimes called the Fermi paradox. If intelligent civilizations are common, where are they? Why have we not detected them? Possible explanations range from the hopeful to the unsettling. Perhaps intelligent life is extremely rare. Perhaps civilizations are separated by enormous distances. Or perhaps we have simply not searched long enough. The answer remains unknown. Future discoveries may transform our understanding of life in the universe. What makes modern science so exciting is that some of its biggest questions remain open. The age of discovery is not over. In many ways, it is only beginning. New telescopes peer deeper into space than ever before. Spacecraft explore distant worlds. Artificial intelligence accelerates research. Biotechnology unlocks new possibilities in medicine. Quantum computers may someday solve problems beyond the reach of traditional machines. Future generations may witness discoveries that seem unimaginable today. History shows that scientific revolutions often arrive unexpectedly. Few people anticipated Newton's laws, Darwin's theory of evolution, Einstein's relativity, or the discovery of DNA before they happened. The next great breakthrough may already be approaching. Perhaps somewhere in a laboratory, observatory, or university, a future scientist is working on an idea that will reshape our understanding of reality. That possibility is one of the most inspiring aspects of science. Knowledge is never truly finished. Every answer leads to new questions. Every discovery opens new frontiers. The story of science is not a completed book. It is an ongoing journey. A journey that began when our distant ancestors first looked up at the stars and wondered about the world around them. And it is a journey that continues today. The greatest discoveries of the future may still be waiting to be found. Chapter 13. The Next Great Discovery. If there is one lesson that emerges from the history of science, it is this. The universe is always stranger than we expect. Again and again, humanity has believed it was close to understanding everything. Ancient scholars thought the Earth stood at the center of creation. 19th century physicists believed the major laws of nature had already been discovered. Even today, it can be tempting to assume that the biggest breakthroughs are behind us. History suggests otherwise. Every generation has uncovered truths that previous generations could scarcely imagine. No one in ancient Egypt could have conceived of a telescope revealing galaxies billions of light years away. No scholar in medieval Europe could have imagined microscopic organisms causing disease. No scientist in Newton's time could have predicted computers, genetic engineering, or spacecraft exploring distant planets. The future will almost certainly surprise us in the same way. The question is not whether major discoveries remain. The question is, which mysteries will be solved next? One of the most promising frontiers is artificial intelligence. For centuries, intelligence appeared to be uniquely human. Machines could perform physical labor, but thinking remained the domain of the mind. That distinction is beginning to blur. Modern AI systems can recognize patterns, translate languages, generate images, analyze enormous data sets, and assist scientific research. They're already helping scientists discover new materials, identify potential medicines, and process information at scales impossible for individual humans. Some researchers believe AI could dramatically accelerate scientific progress during the coming decades. Instead of replacing scientists, these systems may become powerful tools that help uncover patterns hidden within vast amounts of data. The result could be faster breakthroughs in medicine, physics, chemistry, and countless other fields. Medicine itself stands on the verge of major transformation. For most of history, doctors could only treat symptoms. Today, scientists increasingly understand disease at the genetic and molecular level. Researchers are developing therapies that target the root causes of illnesses rather than merely managing their effects. Gene editing technologies such as CRISPR have already demonstrated the ability to alter DNA with remarkable precision. Diseases once considered incurable may someday be prevented or corrected before they can cause harm. Cancer treatments continue to improve. Personalized medicine allows doctors to tailor therapies to individual patients. The possibility of significantly extending healthy human lifespans is now being studied seriously by researchers around the world. Yet medicine faces challenges as well. New diseases emerge. Bacteria evolve resistance to antibiotics. An aging global population creates increasing healthcare demands. Future discoveries will be needed to address these problems. Meanwhile, humanity's exploration of space is entering a new chapter. The moon, once the ultimate destination, is increasingly viewed as a stepping stone. Several nations and private companies are developing plans for long-term lunar exploration. Some envision permanent bases on the moon. Others are focused on Mars. A human mission to Mars would be one of the most ambitious undertakings in history. The journey would take months. Astronauts would face isolation, radiation exposure, and extreme environmental conditions. Yet many experts believe such missions are achievable within the coming decades. If humans eventually establish settlements beyond Earth, it would represent a turning point comparable to the first migrations of our distant ancestors. Human civilization would become a multi-planet species. Astronomy is also advancing at an extraordinary pace. New telescopes are allowing scientists to peer farther into the universe than ever before. Researchers are detecting planets around distant stars and analyzing their atmospheres. Some of these worlds may possess conditions suitable for life. The search for extraterrestrial life is becoming increasingly sophisticated. Future instruments may detect signs of biological activity on distant planets. The discovery of life beyond Earth would rank among the greatest scientific revelations in human history. It would transform our understanding of ourselves and our place in the cosmos. Physics continues to pursue answers to some of the deepest questions imaginable. Scientists still do not know what dark matter is. They do not fully understand dark energy. They have yet to unite general relativity and quantum mechanics into a single framework. These mysteries suggest that our current understanding of reality remains incomplete. Future discoveries may reveal entirely new aspects of nature. History shows that the most revolutionary breakthroughs often arise from unexpected directions. The next Einstein may already be alive today. The next Newton may currently be a student asking questions that nobody else has considered. The next great discovery could emerge from a laboratory, a university, a spacecraft, or perhaps from an idea that has not yet been imagined. This is what makes science unique. Science is not merely a collection of facts, it is a process. a method for exploring the unknown. Every answer creates new questions. Every solved mystery reveals deeper mysteries beyond it. The history of science is therefore not a story with an ending. It is an endless journey of curiosity and discovery. From the first humans who studied the stars to the researchers building advanced telescopes today, people have shared a common desire to understand the world around them. That desire has carried humanity from stone tools to space stations, from myths about nature to mathematical descriptions of the universe, from ignorance of germs to modern medicine. The greatest scientific discoveries changed not only what we know, but how we think. They taught us to question assumptions, to test ideas, to follow evidence wherever it leads, and perhaps most importantly, they taught us humility. Every generation discovers that the universe is larger, older, and more complex than previously believed. Yet each discovery also expands the horizon of what humanity can achieve. The story of science is ultimately the story of curiosity, a story that began thousands of years ago and continues today. And somewhere beyond the limits of current knowledge, the next great discovery is waiting.